Okay, right. Discrete mathematics, and we're going to be doing a couple of things. But first things first, let's just peruse through the structure of the exam and the kinds of things that must be known in this exam. And we are getting started now. Right. The part of the exam that is at the beginning is the one on graphs. So we shall focus on the graphs. Right. The student must be in a position to draw a graph. So here's one question that says in A, draw a graph with degree sequence. Okay, we shall discuss this and shall discuss what the degree is of a graph. Because given a graph, you can actually associate, you can define the term, the degree of a vertex of a graph. Right, so we have the degree sequence 1, 1, triple 1, and triple 2. And so, or say why no such graph exists. In B, we have triple 1, and we have triple 3, or say why no such graph exists. Okay, first things first, we are going to look at part A. Right, let's look at part A. Right, but A focuses on the idea of the, what do you call a degree sequence. So a degree sequence is basically a sequence of the degrees of the vertices of a graph. Okay, now, if that is given, first I will just make mention of the following. The number of edges incident to a vertex is called the degree of the vertex. So the number of edges incident to a vertex is called the degree. So what have we just defined? We just defined the term degree. Right, so without wasting time, let's dive into the question. And so in view of the fact that if you draw a graph with degrees sequence that, it is very important for you to note that you have the degrees 1, 1, triple 1, and you have triple 2. So the question we're asking is, does such a graph exist or not? Okay. There is a theorem we use. This one is called the first theorem of graph theory. Theorem. Okay, these are the things you're going to see in the exam. The first theorem of graph theory. What does this theorem say? If V is a graph of size M, then the sum of the degrees of a vertex V, where V is an element of the vertex set of G, and this is equal to 2m. Okay. So this means the sum of the degrees of the sum of the degrees of the graph G is even. It's an even number. It's an even number for a graph of size m. Okay, for a graph of size m. Right, so just note that at the moment. Now we ask the question if this graph indeed exists or does not exist. Right, we get to analyze this very, very carefully. You get to analyze this very, very carefully. Right. I want to also do this here. The number. So this is just a theorem. Right. So let's look at this one. What is the size of a graph? The number of vertices in a graph G is the order of G. And the number. So we have defined the order of G as the number of vertices in a graph G. And the number of edges in the is the size of G. We define the number of edges to be the size of G. So if we want to state the size of G, we are speaking about the number of edges. The number of edges is the size of G. Okay, this is enough. Then what do we say here? What do we say? Then here's the question. The question is clear. And it's saying, you need to draw a graph with the degree sequence 1, 111, and then you have 222 that way. But if you add the sum of the degrees, the number must be even, which must be twice the size of G, where the size remains refers to the number of the edges. But you can see here, if you add all the degrees, here, the sum of the degrees. Here, the sum of the degrees is what? Here, the sum of the degrees is what? We'll continue. Okay. Okay, the sum of the degrees. Here, the sum of the degrees is given by 1 plus 1 plus 1 plus 2 plus 2 plus 2. So just add the degrees. But here, what answer do we get here? We have 3 plus 6 is 9. Impossible. Because according to the first theorem of graph theory, the sum of the degrees must be an even number. Impossible, since the sum of the degrees must be an even number. And 9 is odd. Hence, no such graph exists. Hence, no such graph exists. Okay. Right. So obviously we're asked to draw this graph, but we can't draw this. It does not exist because the sum of the degrees must be an even number, but clearly it is 9, which is an odd number. Part B of question 1. The exam is like this, and the exam that's going to be written is going to follow this structure. Right. So you need to add the sum of the degrees. But now, obviously, in B, we can see that if you add all these, you have 3, 6, 9, and then you have 12. So here, note that the sum of the degrees note that the sum of the degrees is 1 plus 1 plus 1 plus 3 plus 3 plus, which is 12, which by definition must be equal to 2 into 6. And thus we are dealing with a graph. We're dealing with a graph of size 6. And therefore, we are dealing with a graph of size 6. Okay, so here we're dealing with a graph of size 6. We're dealing with a graph of size 6. Okay. Um. Yes, of size 6 according to the first. According to the first. Right. According to the first theorem of graph theory. According to the first theorem of graph theory. Okay. We continue to answer this question. Now we need this graph of the degree sequence 1, 1, and then 3, 3, 3. You can draw a bridge. Here you have these. Okay. Now at this point, you can see these are the case. This is the case. So this is degree one, degree one, degree one, and then degree three because the incident edges here are actually three. The incident edges here are three, and the incident edges here are three. So as a consequence, then you have there are three vertices of degree one, and there are also three vertices of degree three. So we have constructed that graph there. So the graph, this graph in B, indeed does exist. Right. Question two, you need to deal with, the student must be able to deal with isomorphic graphs or graphs that are not isomorphic. Determine whether the following two graphs, G and H, are isomorphic or not. Okay. Right. Sure, I've created a bit more space here. Okay, we can, that's okay. Right, I can elaborate a lot on this one. But first things first, I will um, state something very, very important about the idea or the notion of the isomorphism of graphs. Let's state the theorem about two graphs that are isomorphic first. So two graphs G and G primed are called isomorphic. The two graphs G and H or G and G primed, you can call them two graphs G and H. Two graphs, let's call them G and H. You can call them G and G primed, but in this case, it's easier to just call them, it's more relevant. Two graphs G and G and H, excuse me, are isomorphic if there exists a one-to-one correspondence between the vertices in G and the vertices in H, such that such that okay, right, such that a pair of vertices are adjacent in G if and only if their corresponding pair of vertices are adjacent in H. Right. Two graphs G and H are called isomorphic if there exists a one-to-one correspondence between the vertices in G and the vertices in H, such that a pair of vertices are adjacent in G if and only if the corresponding pair of vertices are adjacent in H. Okay. That is the definition of isomorphic graphs. We ask the question, we need to determine, in this case, whether the following two graphs, that the G and H, are isomorphic or not. If they are, give a vertex correspondence. If they are not, give a reason why. Okay, I need to state up front. That in this case, write G and H are not isomorphic. Are not isomorphic, and analyze why. Okay, we note therefore that G and H are not isomorphic. Why is this the case? There are a couple of reasons and we state them. The vertex adjacency is the reason here. The vertex of degree 2 in H. Okay. So you can see that there's a vertex of degree 2 in H. Is part of a triangle. Whereas the vertex whereas the vertex of degree 2 in G right, so here is the vertex of degree 2 in G, and you can see that the vertex of degree 2 in H is part of a triangle. There you go. But now here, the vertex of degree 2 is the vertex C. And the vertex C is not part of a triangle. Okay. The vertex degree 2 in G is not. Now, because of these, the two graphs are not isomorphic. And then you get your marks. So what is the answer to this question? Obviously, this part here, where I just defined isomorphic graphs, it's not important. Well, it's not to be. You don't need to be defining things in the exam quite. You need to answer the question, by and large. So we state therefore that the two graphs G and H are not isomorphic graphs because the vertex of degree 2 in H is part of a triangle, whereas the vertex of degree 2 in G is not. All right, we're done. Next question. Right, so the idea of what you call a Hamilton path. Hamilton path. Right. So I have made space available there. The idea of a Hamilton path. Right. So we discussed the idea, this notion of a Hamilton path. Hamilton path. Right. Let's discuss this notion. Let's spend some time on this notion here. Right. Let's spend some time, just a few minutes on it now. Right. But first, I want us to just to think about what this is, in essence, you know. Right. What this is, in essence. Right. Okay. All right. I want us to explore what this is in essence. Okay, I want us to explore some background information that we need to know, so that we can be in a position to make a reasonable amount of progress in answering these, and also get to understand these a little bit more. Okay, right. Um, there are a couple of descriptions of these that are equivalent, but I want us to have a common understanding of this. Right, I want us to have a common understanding of these. Right, just a second. I'm gonna give a description now of these as significant entities. But first, we give a description. We give a description. And here is the description. It goes as follows. A path in G that contains every vertex. Every vertex of G is called a Hamilton path of G. Okay, so a path in G that contains every vertex of G is called a Hamilton path of G. All right, right. Hamiltonicity and Hamiltonian graphs. Okay, but I want to have a description of certain graphs are called tough graphs. Okay, that's advanced. But first, I want us to discuss the idea of a circuit. Right. This us discovers the idea of a circuit. Right. So we're going to now discuss, just have a description, some definition of a Hamilton circuit before, just so that we can have some understanding of this. Right. In terms of what a Hamilton circuit is, okay, because it's very important that we understand a Hamilton circuits, okay, and just a circuit, obviously, in general. What is a circuit? Right. Because in this case, we must state that no Hamilton circuit exists. But now we understand that the Hamilton circuit will certainly be a path that is closed. Okay, so we're going to discuss the notion of closed paths and open paths. Right. Okay. I'm going to write a description that's very succinct here. Very, very succinct in a little bit. Right. Okay, let's write the following. Let's write the following. So you can define this in many ways, so let's just get started with these. Okay, you can define it in terms of walks. Okay, so you can trace these. So a Hamilton circuit. A Hamilton circuit. Right, if you look at a Hamilton circuit, how do we define this? If there is a walk, in the connected graph, if there is a walk in the connected graph that visits every vertex of the graph, exactly once, except starting vertex. Okay, except starting vertex, except starting vertex, without repeating, without repeating the edges and returns to the starting vertex then such a such a walk is called a Hamilton circuit. Okay, so this walk, it's just the notion of a path that is traced, a path that one traces. Right, we get to answer this question now. We've just laid some foundation. Right, so I would like us to use their rules. There are three rules that we use. So first, so we're going to look at rule number one. If a vertex X has degree 2, both of the edges incident to X must be, I put the graph there. I did. Okay. Rule number one, if a vertex X has degree 2, both of the edges incident to X must be part of any Hamilton path or Hamilton closed path circuit. Right, next we'll look at rule number 2. No proper subcircuit. Okay, no proper subcircuit that is, what does this mean? That there must be no proper subcircuit. What does this mean? Well, it means that is to say, if there is a circuit not containing all vertices can be formed. Can be formed when building a Hamilton circuit. Rule number 3. Once the Hamilton once the Hamilton once the Hamilton circuit is required to use 2. Right, once the Hamilton circuit is required to use 2 edges, to use two edges. At a vertex. Okay, I'm going to give the answer just now. I'm just laying some foundation so that when you speak about the rules, you can know which rule that is. Vertex X, all other unused. All other unused edges. All other unused edges. Incident at X. Okay, let me just get my marker. Right. Continue. Right. You continue. Just need to clear this up. Right. Incident at this one. Incident at X. Okay, we'll just analyze what all this means. These are just the rules. Must be removed. From consideration. Must be removed from consideration. All right. Okay, we continue. Must be removed from consideration. All right, we're here. Right, what does this mean? And now we analyze and move on to the next thing. Move on to the question. Right, so we have rule number 3, like that. Rule number 1, if a vertex X has degree 2, just quickly, I'm just passing through this, both of the edges incident to X, right, must be part of any Hamilton circuit. Rule number 2, no proper circuit, that is a circuit not containing all vertices, okay, can be formed when building a Hamilton circuit. So you cannot have a proper circuit there, okay? A proper circuit being the one that contains all the vertices. Rule 3, one of the Hamilton, once the Hamilton circuit, right, I wanted to obviously write once there. So once the Hamilton circuit is required to use two edges at a vertex X, all other unused edges incident at X must be removed from consideration. Okay, we have laid enough foundation. Find a Hamilton path and prove that no Hamilton circuit exists. 7 marks. Let's dive into the question now and answer it. I've made space available here to write a lot of these things here. So here is the answer. We're looking at still question 3. One Hamilton, this is the actual solution to the question. One Hamilton path is, let's look at A, B, C. So you have A, B, you move from A to B, and then to C. and then to G, and then to E, and then to H, and then to J. Okay, and then you move on to D, move on to F, move on to I. So surely this one visits all the vertices. So one Hamilton path is A, B, C, D, E, H, J, D, F, I. We use um the three the three rules. Okay, we call them the three rules of Tucker after the author of the book. And if you check in the book, you can find those on page 57. We use these to show that a Hamilton second does not exist. To do that, you're going to say consider vertex J. Consider vertex J. Okay, let's look at vertex J, this one. We have seen that we have had one path that passes through all the vertices and it therefore qualifies to be called a Hamilton path. But if we consider vertex J, like we've encircled it there, right, we know that by symmetry, we can consider the case where CJ and DJ, okay, let's look at the case where we look at CJ as a path and also DJ as a path. So we can consider the case where CJ and DJ right, CJ and DJ form part of the Hamilton circuit. Okay, let's look at this. By rule number 3, we have to delete JH. Right. By rule number 3, we have to delete JH because rule number 3 is clear that you can't repeat. Right. But most importantly, rule number 3 says once the Hamilton circuit is required to use two edges at a vertex X, all other unused edges incident at X must be removed from consideration. So we have to delete JH by rule 2. By rule 2, we have to delete right, we have to delete right, we have to delete CD. Okay, think about that. But now I want to state, therefore, that we can consider let's consider vertex A, for example. Here is vertex A. By rule number 2, okay, here is rule number 2. No proper subcircuit. And that means that a circuit not containing all the vertices can be formed when building a Hamilton circuit. So we cannot have, we were saying there must be no proper subcircuit. So now, by rule number 2, right, by rule number 2, we have the following. Consider A. By rule 2, we cannot use both AC and AD. By rule number 2, we can't use, if you consider vertex A, by rule number 2, we can't use both AC and AD. By symmetry, we can consider the case where we use AC and AB. By rule number 2, all right, first and foremost, by symmetry, we can consider the case where we use AC and, let's look at that, AC and AB. AC and AB. Okay, we'll analyze what that means just in a little bit. And what the reason for this kind of reasoning is. Right. AC and AB. By rule number 2, we have to delete we have to delete BC. Right, to avoid a proper, there must be no proper subsecond, so we have to delete BC by rule number 2. Right. We therefore notice that we are forced to use, we are forced to use, not used. Right, so we're forced to use right, so we're forced to use. Right, we note that therefore that we are forced to use the following. We're forced to use BD. Right, we become forced to use BD. SB now only has SB now only has degree 2. Degree 2. Yeah, B is going to have degree 2 if you delete BC. For example, as stated. As degree 2 by rule 1. Okay, we just saw rule 1. Okay, here is a very interesting discovery with this reasoning. But then we have a proper, okay, we need to spend a bit of time on these kinds of questions. We have a proper subsecond. Subsecond ABD JCA. Right, we realize in view of this, let me use green. Right, but then we have a proper subsecond A, B, D, J, C, A. Okay, we have a proper subsecond. And so we therefore note that, as stated in this case, the question said find a Hamilton path, which we did, we found, and prove that no Hamilton second exists. And we have gone on to prove that no Hamilton second exists. Right, so we have that. But I want to state something else. Right, okay, I'm going to state um, more properties of Hamilton seconds, etc. I'm going to emphasize this. at some point. Okay, question 4, it will always be on the chromatic numbers and coloring, graph coloring. So we need to color graphs in certain colors, and we make our graphs very colorful. And this gives birth to something very interesting. We call right. There's a topic that will it's very interesting in mathematics. Yeah, and I'm gonna state this topic on more counting techniques, etc. Okay, more counting techniques. But yeah, there's a topic I'm gonna speak about there. Okay, but first let's look at this. Right, chromatic numbers. If you consider the following graph, this one here, determine the its chromatic number. Give a minimal coloring and a proof that a smaller number of colors is not possible. Okay, normally we argue this. Let's look at this one. Right, so if you look at question 4, we are looking at the idea of what we call a chromatic number. Right, so obviously no one is going to ask you what a chromatic number is, so let's dive into this actually and answer this question. Right, so what is the chromatic number at this point? Okay, very, very interesting observation. I'm going to do it on this side. Right, so we're going to note that we're doing 4A. Since they are triangles, okay, the triangles are very important because the triangles tell us that the chromatic number chi of G must be at least 3, must be 3 or more because of the 3 vertices. So now you can, the colors that are possible, they can only be 3 colors or more. 3 colors because there are 3 vertices, and in a triangle the colors must be different. You can't have adjacent colors that are the same. So because of that, then we have 3 for the triangle or more because of the extensions of the graph. Now we continue. So we consider, let's look at triangle. Okay, we start um, at A. Let's start at A. Right, you started A, here is A. Move to B. Move to D. And then move back to A. So consider triangle A, B, D, then A. So this forms a circuit. Right, so let's start coloring now. So you're gonna color A blue. So here you associate a blue color. Yes, associate a blue color with A. And then B, make it green. Make D red. Okay, so you have blue, green, red. Then you go back to blue, A. Right, so we have that. Right, so color A blue, B green, and D. Okay, you make D red. Then C has then C has to be, so we think about C now. Right, so if you color them like this for a start, then what is the color C? So C can only be blue because now it can't be green, it can't be red because you already have those colors adjacency. So it can only be blue. So we're forced to allocate the blue color. So then C has to be blue. H. Okay, if this one is blue, then C has to be blue. H, green. H, green. Okay, obviously, if you have blue, red, H can only be green because it can't be blue because then you can't have blue adjacent blue, but also it can't be red, so it can only be green. So H is green. And now, what about E? What about E? E is very interesting. Now E is adjacent. So now we have a challenge. You know? Now E is adjacent to a blue because you can see if you're E, there's blue, there's red, there's green. So it's adjacent all of them. So it's forcing us to introduce another color. So now E is adjacent to a blue, green, and red. Vertex, vertex. E now is saying that we need another color. And therefore, a fourth color, now we can introduce another color. Say yellow. Say yellow is needed. Okay, so we need a fourth color, so we're gonna make this one yellow. Because it can't be green because it's already green adjacent to it. Can't be red, etc. Okay. So now this means we have a four coloring. A four coloring of G is as follows. Right, let's look at the four coloring. So we have the blue, we have the green, we have the red, and yellow. So the blue, A and C. We have seen that A and C are blue. What about green? Green where B is green, but also H is green. Yes, and what? And F. You can make this one also because once you make this yellow, then you can make this one here. So you have blue, yellow. So you can make F green as well. So you can make F green. If you make F green, what about red? Which one's a red? D is red. Vertex D is red, but also vertex G. Okay, because once you make these colors here, what are the possible colors of G? G now is here. You can see there is green, there is yellow, that is those which are adjacent G. Right, so G is the one we chose to be yellow. All the vertices covered. What? Yeah, because I was saying G needs to be red because now it is adjacent B, which is green. Okay, but also we chose H to be green. And so, but now G is also adjacent, so it can only be red because it can't be any of the colors. Okay, think about that. Hence, the chromatic number of G is what? Is 4. Hey, there it is. The chromatic number of G is 4. So you look at the 4 coloring. So it means something. It means, therefore, when you are dealing with these, you need to think very carefully and make sure that you understand these and you interpret these correctly. But also, what is important here? You don't need to be writing a lot of the things. So you need to just say, since they're triangles, you see a triangle, so the chromatic number of G is at least 3. 3 or more. And then the next thing is you work on these coloring here. So you just put blue, etc., etc., and then you come in and do this table here. You show that you show the 4 coloring, the fact that there are 4 colors, and these 4 colors will color all the vertices. So no vertex is left out. We're done. So in other words, the chromatic number of G is equal to 4. Right, so we are looking again at the same question, the same graph, but a different question. Use the second chord method. Use the second chord method to determine whether the graph is planar. If it is planar, give a planar drawing. If it is not, give a subgraph which is a K33 or a K5 configuration. Okay, so let's look at the second chord method. Hey, interesting circles in school or at university. Right, to do the second chord method for this one, we need to identify a Hamilton circuit. So we're looking at 4B. A Hamilton circuit is, what is the Hamilton circuit here? Okay, let's choose one Hamilton circuit. So you can start with A, go to B, go to C, okay, go to D, go to H, go to G, go to E, go to F, go to A. So this is a Hamilton circuit. So a Hamilton circuit is A, B, C, D, H, D, E, F, A. So it goes back, you go back to A, so its circuit is closed. So because of that, then you're going to make this drawing. Right. After we've made this drawing, then you're going to start. We put a node here, a vertex, then we put A. Another vertex, B. A vertex, C. Another vertex, D. A vertex, H, according to the circuit, Hamilton circuit. A vertex, G. A vertex, E. A vertex, F. Okay. We have this. Then from F, we go back to A. Right, there's something we call the inside and outside symmetry. So by inside, inside, outside symmetry, we choose AD. Okay, let's choose AD. We choose AD to the inside. Let's look at what that means. By inside outside symmetry, we choose AD to be inside. By inside outside symmetry, we choose AD to be inside. So in other words, you have AD, we choose it to be inside. So we're going to draw it inside. Inside the circle. There we go. We've just drawn that. We choose it to be inside, so we've drawn the line segment there. Then there's FC. Right. So if we were to now look at F and C, they must not cross. We avoid crossing. So FC must be outside. Why must it be outside? Well, FC must be outside because it's going to cross. So, okay. FC must be outside. Then, okay, we have that. What about BG? Let's look at B and G. Then BG, right. Then BG. Here is B and there is G. Then BG cannot be drawn. Why? Because it's going to cross. Either if you draw it inside, it's going to cross. BG. If you draw it outside, it's still going to cross. It cannot be drawn. Then we say then BG cannot be drawn. A K33. A K33 configuration is a K33 configuration. Let's look at the K33 configuration. So we have the vertices here. We have the vertices. So we have these vertices. So we have the vertex A, C, G, B, D, F. And then we join these. B to C, B to G. And then now you have A to D, A to F. Okay, so you have A to B. We have, yeah, okay, continue. There's B to G. B to G, no, rather D to G. Right. Let's see now. What are we getting here? There's also FC. There's also FC. Let me see. Mhm. Right. So a K33 configuration, therefore, means what? Obviously, you can see that we've taken care of a total of 6 vertices here. Right. So the 6 vertices are not everything because there's some other vertices that are not there. So the K33 configuration is very possible. So you can put, like, if you look at DG, 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 you can put H. So in other words, if you look at DG, you can via H. In other words, DG, you can via H. You can put H here. Then GF, right? If you look at GF, how else can you get to GF? So you can via E, for example. Yeah, you can go through E. So this is a possible K33 configuration. It's a possible K33 configuration. Right. Okay. But most importantly, in view of the Hamilton circuit, you can see that we said A, B, C. So you have A, B, C. Then we have D, H, G. A, B, C. Then you go to D, H, G. Then you go through E, F, then A. Right. So this is a possible K33 configuration that is using the Hamilton path we suggested. So yes. So obviously the question in 4A and 4B was, use the second chord method to determine whether the graph is planar. If it is planar, give a planar drawing. If it is not, give a subgraph, which is a K33 or K5 configuration. Right, so we have seen that it is not planar, and therefore we've given a K33 configuration. We continue. Now, if you look at C, Consider the following graph, G, same graph. Determine whether it is bipartite. Right, if it is bipartite, a bipartite graph actually is a special kind of graph. You state any theorems used. Okay, shall determine that one. Let's analyze these together. So we are dealing with 3C, 4C, excuse me. Right, we are putting it that it is not a bipartite graph, not bipartite. As it contains it contains 3 seconds because of those triangles. Okay, so it is not bipartite because it contains 3 seconds because of those triangles, right? So because of that, it is not bipartite, but I'm going to elaborate more on the bipartite graphs. But I want to state here that here is the definition, very important definition. So a graph G is bipartite if and only if, goodness me, let me remove this. A graph G is bipartite. That's the condition. That helps us to see a bipartite graph because they don't look bipartite. I'm going to draw just a typical bipartite graph. But a graph G is bipartite if and only if and only if. Every second, every second in G has even length. Okay, that's the thing. So a graph is bipartite if and only if every second in the graph has even length. But obviously you can see that we have those 3 seconds here because of the two main triangles. So not every second has even length. Some have length 3. So because of that, then this graph is not bipartite. So you look at the length. Okay, let's look at the next question. Consider the following graph. Determine whether it has an Euler cycle or Euler trail. Now let's look at the Eulerian graphs. Right, let's look at the Eulerian graph. Now there's a theorem we use here. I want to state it because it becomes very easy. Very, very straightforward to just identify these Euler trails because they are there already in the exam, these ones. Euler cycle, Euler trail. I'm going to state the actual condition we use, the theorem we use, and then we can easily be in a position to just extract that one. Just extract that one there. Right. There it is. I want to state this condition. There's a theorem. A multigraph has an Euler cycle if and only if it is connected and has all vertices of even degree. Of even degree. Okay. So this gives us a multigraph has an Euler cycle if and only if it is connected and has all vertices of even degree. What about an Euler trail? Sure. A multigraph has an Euler trail, but not an Euler cycle. But not an Euler cycle if and only if and only if it is connected and has exactly two vertices of odd degree. Okay, a multigraph has an Euler trail. When does a multigraph do not be threatened by the notion of a multigraph? It actually refers to basically a general graph. A multigraph has an Euler trail, but not an Euler cycle if and only if it is connected and has exactly two vertices of odd degree. So, so you need to determine whether it has an Euler cycle or Euler trail. So once again, Euler trail means two vertices of odd degree. Okay. An Euler cycle means that it is and connected and has all vertices of even degree. So Euler cycle means every degree is even. So every vertex has even degree. Now, let's analyze and see what is happening here with the question. We note that since, since G has exactly two vertices, okay, it has exactly two vertices D and E of odd degree. Of odd degree. Since G has exactly two vertices D and E of odd degree, it has an Euler trail. Since G has exactly two vertices, D and E of odd degree, because if you check this one, all right. If you look at D and E, okay, just a second. Yes. Since G has exactly two vertices, D and E of odd degree, this is correct. It has an Euler trail, but no Euler cycle. But no Euler cycle. Since G has exactly two vertices, D and E, okay, because if you look at D 2, 4, 5, so you can see there is degree 5, 2, 4, 5. So we can see here there's degree 5, both of them. So which is odd, right? Because the rest of these are degree 4, degree 4, degree 4, degree 4, degree 4. Since G has exactly two vertices D and E of odd degree, it has an Euler trail but no Euler cycle, according to this theorem. A multigraph is an Euler trail, but not an Euler cycle if and only if it is connected and it's exactly two vertices of odd degree, exactly two. We have that. It has an Euler trail, but no Euler cycle. All right. Okay, we have this one now. We'll move to the next question. Right, let's look at E. Letter E, you consider the same graph G. We've just gone through this graph, so we are very familiar with this graph. We actually at this point now understand this graph better. We have dealt with it. We have done a lot of counting based on the graph, chromatic numbers and other things. Determine the number of edges in the complement of G. In the complement of G. But first things first, the number of edges in G, the number of edges in G is. Okay, let's look at the number of edges in G. We count them in order. So we shall count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Hey, so the number of edges in G is 17, 1, 7. The number of edges, the number of edges in K8 is? Okay, because we can see that there are 8 vertices here. And K8 has the following. Okay, there's maximality because this is the complete graph. This K8 stands for the complete graph on 8 vertices, which has the most edges. So it has 8 by 8 minus 1, 7 over 2. So the Kn would have n minus 1 over 2. And if you, this is saying 8 divided by that is 4 by 7, which is 28. So in other words, the complete graph on 8 vertices has the most edges and has 28 vertices. So now we want to count here. Hence, the number of edges in K8. Hence, the number of edges in K8 is, that's not what I want to say. I want to say the number of edges in the complement. Hence, the number of edges in G complement is, right. So the complement would therefore be 28, which is the most number of edges on a graph on 8 vertices, minus 17. So for the complement, then you get exactly 11. So which means the number of edges in the complement is exactly 11. Okay, there are many ways to do that, but you can also draw the complement and start counting. You can look at the complement graph and start counting. You can always look at that as well. We'll spend some time on drawing complements of graphs. Now we look at this one here. A very important notion on the breadth first search, free, starting at vertex H. So also this one is a very, very important concept that is in the exam almost all the time. All the time. So let's look at this one. Let's look at this one. Okay, now analyze this together. Determine the breadth first. Search. Free, starting at vertex H. We're going to begin at H. Right, so if you start at H, you begin at H. Here is H. Right, so if this is H, you can actually now consider the following. So from H, we go to From H, you can either go to C, or from H, we can go to D, or from H, you can go to E, or from H, we can go to G. Right. Okay. Or from H, you can go to E. Okay. And then, so we can see that we have used the breadth first because we're not going down, we're just going broadly. To the left, down, towards the right. So that is the breadth first. Right, sorry. Um, we continue. We continue. Okay, let's continue. If you are at C now, you can go to B. You can go to B. If you're at C, you can also go to, what else can you go to? If you go, you can also go from C to F. If you're at C, you can either go to B or you can go to F using that edge there. Or if you are at D now, let's look at somebody at D. You can go to A. If you're at D, you can go to A. Goodness me, you can go to A. If you're at D, you can proceed to A. Okay, let's look at that. All right. This one is B. Excuse me. If you're at C, I wrote D here by mistake. Or if you are at C, you can go to B as an alternative. If you're at C, you can go to B. Or if you're at C, you can go to F. But if you are at D now, you can go to A. Because B is already mentioned. So you need to go to A. If you are at E, let's look at somebody at E. Where can you go to? Right, a couple of ways to consider because now you moved from H to E. So, but A has been mentioned if somebody wants to move to A. Or can you move to D? D has already been mentioned adjacent E. Can you go to F? F has already been mentioned below E. Or this determine the breadth first search tree starting at vertex H. Starting at vertex H, this tree diagram is complete. Okay. Next question. Next question. Okay, just looking if everything is okay. It looks okay. Right, so we move on. This is A. Right, go to the next question. Okay, this question is there most of the times. Draw all 9 isomorphic, 9 vertex binary rooted trees, indicating the root in each case. indicating the root in each case. Okay, what is this? Let's understand this. So this is a very, very interesting one. So um, we'll think about these together. And we're going to write down the answer just now. Um, there are a couple of things that we learn, and there are a couple of things that they are what we call the MRE trees. They are the NRE trees, and now they are rooted trees. Okay, just going to mention some of them. Their parent, the trees have parents. Some of them have children, and now they are binary trees. So I'm just going to mention this. I'm just going to mention this. Okay. Vertices of T with no children are called leaves. Vertices with children and internal vertices. Right. I want to give an example of this tree. Right. So if m equals 2, then you have, okay, I'm just going to mention, I want to mention something here. Just 1 second. Just 1 sec. Right. I'm just going to write something now. Very important for us to proceed. And right. 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 So in other words, I want to give this binary tree. Let me just say this. Binary tree. The tree that has two children. Right. Right, right, right. So a binary tree would just be a tree with a root like this, generally. So in other words, you have 1, 2, 3. Okay, so obviously you're dealing with a binary tree here. So a binary tree, therefore, would just be an example. This is just an example of a binary tree, but no one is going to ask you what that is. So there can be 3 array trees with 3 branches, etc. Right. Okay. I'm just going to give more. Right. Okay. This is just an example. Doesn't mean that is the only one. Right. So draw all non-isomorphic 9-vertex binary rooted trees, indicating the roots in each case. Okay, let's look at this one. All of them. So we're going to start with 3T1. 3T1 has, for instance, the root. And 2 children. Okay, and then if this tree has its root and 2 children, okay, I can use those concepts loosely, but you need to understand, you use those. Right, so if in this one, 2 binary, and then now these are vertices, this. And this one, that is the root. There's another one, T2. Okay, we have a root. Another tree, we call it T2. Binary, two children. Call it a two-array tree. Two-array tree. Then they're called M-array trees. And then it's a two-array tree with two children at a time. Right, so you have this one. And then now this one goes like this. And this goes this way. Okay, so T2, you have the root. And that. Okay, 9 vertex. 2, 4, 2, 4, 6, 8, 9. 2, 4, 6, 8, 9. And then now there's tree number 3. Can have a root. With two children. Two children here. Two children. Two children. Two children. Okay, so you have a tree number 3 that looks that way. So now non-isomorphic. Okay, these are special types of graphs. So we have defined isomorphic graphs. That those graphs, the two graphs are isomorphic, G and H, we said if those properties are satisfied there. But now you have those vertices to the same degree being adjacent. In one graph is in the next one. So adjacency becomes but obviously the number of edges, the number of vertices become primary properties. So if two graphs are isomorphic, then they have the same number of vertices and the same number of edges. But obviously, the extra property of adjacency becomes very important. Those degrees, those vertices of certain degrees must be adjacent in one graph as they are in the next one. Okay, we proceed. So if we proceed now, what is this? Okay, we analyze it. We indicated the root in each case. Right, so these are the trees. These are the trees. Okay, I'm gonna give more properties on these trees. Right, I'm gonna give more properties on these trees. Okay, so these are basically all the trees, or 9 vertices, and these trees are not isomorphic trees. Okay, so any other tree that one can draw will be isomorphic to one of the trees here. So just note that. Okay, we move to the next question. How many ways are there to choose a pizza? And 3, not necessarily different sandwiches from a cafe. If there are 4 types of pizza and 5 types of sandwiches to choose from, analyze this together. Let's count. Let's look at this one. Let's look at this one here. How many ways are there to choose a pizza? And 3, not necessarily different sandwiches. So you need to choose a pizza and 3, not necessarily different sandwiches. So some of those sandwiches are likely to can be the same. So they are not necessarily to be different sandwiches. You can decide to choose this is sandwiches that are the same, you know. Right. So if this is the case, then we ask the question, how many ways are there from a cafe? If there are four types of pizza and five types of sandwiches. Okay, let's understand this one. Okay, I want to do this properly. There are a couple of results one is supposed to know here. Then there's a theorem we need to state. What theorem do we state here? There's a theorem we state on this method of counting. Method of counting. Right. What theorem do we state? Okay, I'm going to state the theorem now. Just one sec, because now the theorem is the one important theorem. We're speaking about the types of things. The number. Okay, in mathematics, we learn first the rules before we apply them. The number of selections with repetition of R objects chosen from n types of objects is the number of selections. Okay, we speak about the selections because this is, you need to select, you need to do selections of the sandwiches, the pizza, and so on. This, understand, this is the rule we use here. The number of selections with repetitions. So obviously, you see, not necessarily different. So we can repeat of R objects chosen from n types. So the n types of objects is the same as C R plus n minus 1 R. Okay, that's the formula we use. So, but we need to determine what R is and what n is here. So the n refers to the types. So how many types are here? So there are, you have a given case here. Right, so from a cafe, if there are four types of pizza and five types of what? Of sandwiches. So, but now I want to mention, so because the pizza, you need to choose a pizza and there are four types of pizza. There's the answer to the question. There are four ways to choose a pizza because there are four types of pizza. You can either choose type 1, type 2, type 3, type 4. Right, you need to choose a pizza. But now you need, now the problem here, you can have repetitions. You need to choose three sandwiches. And there are five types of sandwiches to choose from. So they are C into R plus n minus 1 R. What is this? Um, the types of the sandwiches. Right, there are 5 types of sandwiches. So you have n equals 5 types of sandwiches. Types of sandwiches. And then are objects. So, but there are 3 sandwiches. What you must deal with? Yes. Oh, okay. Sandwiches. So which means that you have 3 plus 5 minus 1. 3. What is the answer? So this is number of ways, which is C. Okay, leave it like that for now. This number of ways to choose 3 sandwiches. What is the number of ways to choose the sandwiches? To choose 3 sandwiches. The choices of pizza and 3 sandwiches. Okay, so we continue. The choices of pizza and 3 sandwiches are independent choices. So these are independent. So the number of ways to choose a pizza and sandwiches is, those are independent, therefore you multiply them. So it's 4 times the combination of the 3 plus 5 minus 1, choose 3. And this is 4 by 7, choose 3. And if you multiply everything here, it's going to be 4 by 7 by 6 by 5. And you divide everything by 3 by 2. And it's 140. Sorry, how many ways are there to choose a pizza and 3 not necessarily different sandwiches from a cafe? If there are 4 types of pizza, but you just choose 1 pizza, so there are 4 ways. And the 5 types of sandwiches to choose from, but you choose 3 sandwiches from the 5 types. So you have these. So it's 140 ways. 140 ways. Okay, and we're done with this one. Right, so in view of the time is about 3:15 p.m. And we started at approximately 1 p.m. So yeah, we're doing well time-wise. So I think that we need to take a break. And now we're crafting more of a strategic movement, a strategic plan to get this module covered, at least in the next 2 more days. So we shall see how well we proceed to cover the content. But yeah, okay. So we shall meet again tomorrow at um, 2 p.m. At 1 p.m. 1 p.m. Excuse me. 1 p.m. tomorrow. Okay, thank you. I'll post the video now. Goodbye.